Okay. So I tried to convince you just before that river processes were relatively important to study, and now I will go more into the details of what we know about river processes in terms of river incision and river profile evolution. So I will first discuss about the processes that carves the bedrock, so like in this small gorge here. Then I will show you the different way that people have to study on the field and in experiment those kind of processes. And I will end up with some kind of view on the broad scale and the long river profile and the kind of model we are using or are dealing with, and which kind of broad scale model, which are slightly different from the small scale study. And I will explain why. So people who are interested in river, again, they are numerous. They are sedimentologists, geomorphologists, engineers. Most of them are working on alluvial rivers and sediment transport and to try to understand issues like filling dams, natural hazard, scourings of bridge pier, and whatever. But I will not speak about this issue. First, because I'm not specialist, and second, because I'm more interested in what's going on in the mountain rivers, and in particular, on the evolution of bedrock rivers. So what we call bedrock river, it's a river which has incised into bedrock substratum, and the action of the river to degrade or to dig into its channel, it's to carved into this hard bedrock, not just remove alluvium like the alluvial rivers. So it makes this process is slightly different than for alluvial rivers. So how can we study the mountain rivers and the processes that are acting in mountain river? So there are difficulties. So first difficulties, it's because the incision rate is around, for many rivers, a fraction of millimeter per year. In the high Himalaya, it's a few millimeter per year. Then at the time scale, at the human time scale, it makes a very teeny fraction of evolution. So it's difficult for that reason to study over, for example, a decade of study. In many places, incision is produced by extreme events. So if it can be done, it can correspond to a flood every 10 years or every 100 years. So in that case, during your study, which is a 5-year study, and there is a good chance you missed the morphogenic event. I mean, the event that will produce the erosion. And we will see that the river are complex system with long-term hill slope coupling, so that makes some complexity and difficulties in studying the physical process and the physical models that can reproduce the behavior of bedrock river. Still, despite those difficulties, we can consider different approach. So first approach is go on the field and make measurements. Second approach, try to reproduce in your lab the river systems or part of the river system and make some experimental studies. And last approach, just get rid of all these local complexities and look at broader scale, just at long profiles and compare with regional denudation or uplift rate. So historically, the first observation and quantification on the river network has been done, for example, on map, on long profile, and the third geomorphologists have been deriving mostly scaling laws. So scaling between, for example, the longest river, so it would be this one, for example, and the drainage area. And this produce this kind of scaling law called Hack's law that relate the length of a river to the drainage area. Other people have been looking at river profile and describing mostly the geometric shape of the river profile. So, for example, the concavity. So basically here you have a concavity of 0.5, 0, and 1. So no concavity, so a straight profile, intermediate concavity, and very high concavity. It turns out that many rivers, and in particular bedrock river, the classical concavity that you can find along a river is around 0.5. So in this kind of graph, the concavity corresponds to the slope in the logarithmic diagram between the channel slope and the drainage area. So it is expressed by the fact that the slope of the channel is decreasing with the drainage area to an exponent minus 0.5, and 0.5 corresponds in some way to the concavity. So it is the rate at which the slope is decreasing downstream. So the higher the drainage area is, the gentler the slope is. So there is no mechanisms, no physical explanation. It's just a geometric description of the profile. We can describe also the geometry of the channel widths. And the channel widths of bedrock river can be very different from place to place. So I show you just, for example, here in central Himalaya, across the Geochimiques, a place where the river is relatively large, with a drainage area of 350 square kilometers. But despite this, the channel is narrow, 40 meters. And here, it's a smaller drainage area, 50 square kilometers, but the channel is much wider, 150 meters. So just to show you that we can look at river profile, but we can look also at channel widths, and channel widths, it's also a variable that can vary quite importantly from place to place. But in fact, most of the people consider the channel steepness as more important at than channel width. And for that reason, I will avoid to speak too much about width today, and I will focus more on the channel long profile and channel steepness. So let's go first to the field measurement and experimental measurement about physics of the bedrock erosion. And before that, let's have a quick look at a few basics and on the hydrologic variables. So one of the most used variable in hydraulics, it's what we call the fluvial shear stress. So the fluvial shear stress, or basal shear stress, is the stress induced by the flowing water onto the bedrock, or inversely, this is the force or the stress induced by the bedrock onto the water, on the water. How is it derived? It's just by the making the equilibrium of the force. So consider a particle of water flowing on the channel with some steepness, with some angle alpha, and the slope corresponds to the tangent of the angle alpha. So the equilibrium of the force, so for a fluid which is not accelerated but just moving at constant speed, the equilibrium of the force tell you that the gravity force of the projection of the gravity force on this slope is equal to the friction force at the base of the water element. So per unit of river length, we can derive the gravity force, which is the density of water, the gravity constant, multiplied by the width of the water element, multiplied by the thickness of water, of the depth of water, and multiply, in fact, by sinus alpha. But because alpha in most rivers is very low, we have sinus alpha almost equal to alpha, almost equal to tangent alpha. So most of the time we replace sinus alpha by the slope. And on the other side, we have the friction, which is equal to the shear stress at the base, multiplied by the zone of application of the shear stress, which is what we call the weighted perimeter. So what is the weighted perimeter? It's just if you have a channel in section. So this is the water depth. This is the width of the channel. And the weighted perimeter, it's just the zone of contact of water with the bedrock, so all that area. So for a rectangular channel, the weighted perimeter will be P equal to H plus the width of the channel. Okay? So we have the expression a shear stress equal the density of water multiplied by the gravity constant multiplied by the slope and by R, which is called the hydraulic radius. Hydraulic radius, it's this area of water, which is for rectangular channel H multiplied by W, and the hydraulic radius, it's just RA divided by P, HW plus divided by 2H plus W. For most rivers, and in particular for alluvial rivers, this the width of the channel has this kind of shape. So the width, it's much bigger than the water depth. So in that case, the hydraulic radius is almost equal to the water depth. So in many cases, we will replace the hydraulic radius by the water depth. So we have the shear stress. We consider the discharge expression. What is the discharge? It's just the section of water multiplied by the velocity of the water. And there are also empirical or semi-empirical law that give you the velocity as a function of the hydraulic radius and as a function of the slope. So the steeper is your channel, the higher is the velocity. So it is called the Manning-Strickler relation, but there are other relationship like Shazy relationships that gives a relatively similar result. So combining the discharge expression, the velocity expression, then we can replace this variable into the shear stress expression to end up with an expression of the shear stress, or the basal shear stress, or the friction of water onto the bed, in function of the water density, gravitational constant, a coefficient of rugosity called N, which is depending on the rugosity of the bed. So if you have big boulder, the rugosity is high. If you have a smooth, like cement channel, the rugosity will be quite low. Q, the discharge, W, the width, and S, the slope. So if you know the geometry of your channel, the slope and the width, and if you know the discharge of the water, then at any moment you can compute the shear stress, so the force that the water flowing is making on the bedrock. So why is the shear stress important? Just because the motion of the pebble is directly linked to the force that the flowing water is making on the bed. So if the force is high, then the water will be able to move the bed load, to move the pebbles. And if the pebbles are moved, then they will be displaced, and eventually they will hit the bedrock and produce some erosion. So we suspect that this shear stress variable is important to document the incision of bedrock, and it is also an important variable which is commonly used even in alluvial river to document the transport capacity of a river. So what is the transport capacity of a river? It's the capacity that the river has to transport the bed load, and it's in some way the maximum sediment flux that a river can transport given external condition given by slope and by discharge. So most of the transport capacity relationship are basically introducing one main variable, which is the critical shear stress, which is the dimensionless variant of the shear stress. So shear stress is the basal or fluvial shear stress divided by the difference of density between sediments and water multiplied by G, the gravitational constant, multiplied by D, which is the diameter of the median size of the bed load. So for a given shear stress, if the gravels to transport are a big size, then the shear stress will be low. And in contrast, if the gravels that the river need to transport they are fine gravels, then D is low and the shear stress will be higher. So transport capacity, most of the transport capacity relationship are based or are introducing the shear stress. So basically are dependent on the shear stress. So for that reason, shear stress is quite an interesting variable because it documents how the river can move the bed load and probably how it can erode the bedrock substrate. So just a few examples of this kind of relationships. Transport capacity in function of shear stress. The higher the shear stress is, the higher the transport capacity is. So let's move to field observation and measurement on natural rivers. Yeah? Yeah, the shear stress doesn't depend on grain size. The shear stress, which is a non-dimensional expression of shear stress, yes, it depending on gravel size. Usually we consider the median gravel size or median bed load size.
Will shear stress and the bedrock shear stress are both same or different? Fluvial?
Yeah, well, the shear stress in itself, it can, in the water column, the shear stress, so the horizontal component of the shear tensor, it can be calculated all over the water depth. So it's more or less increasing linearly from the top to the base of the channel. So at the top, it's almost 0, and it's maximum at the base. So usually in the literature, you can find two names for T0, either the fluvial shear stress, to mention it's the shear stress induced by water, or you can find the name basal shear stress to indicate that we are considering not shear stress at the top or medium part, but mostly at the base of the channel. So fluvial or basal shear stress. Yeah.
Same.
Yeah.
No.
So in terms of erosion of the bedrock, several processes have been invoked or proposed and observed. First process, it's pebble abrasion. So each time a pebble is in motion, then when it's hitting or impacting a bedrock surface, it will create a small damage or fracture zone. So this diagram or this image show the microtopography. So we cannot read the scale, but it's a few microns. So in blue, it's a depression. In red, it's small bumps. So it's an experimental impact. So we had a pebble of 8-10 centimeter hitting a marble plate. And so the initial marble was relatively horizontal. And so after the impact, we were able to document the shape of this impact. So we have a depression which is around 2 millimeter. And in fact, if we were able to look at the rocks below, we will see probably many small fractures induced by the impact. So if you imagine the bottom of the river, you will multiply the impact, and each impact will create a small crater and also many fractures. And once you get coalescence of all this microfracture, you will get piece of or chunk of micro chunks of rocks will be eroded. So slowly and slowly, by multiple impacts, you will get erosion of the surface. You can do it by pebbles. Probably you can do it also with finer particles like sand. And in that case, if you go in many rivers, you can see this large boulder sitting at the middle of the river with this kind of feature. So erosion with a smooth surface, and on the other side, some kind of what we call flute cast, and here a slightly sharp transition. And all this smooth surface has been produced by repetitive abrasion by sandblasting. Of a process, if the the bedrock is fracture, so you can see a family of fracture, parallel fracture. And if also there are some weak levels, like when you have a sedimentary units, you may have the weakness along the sedimentary plants. So if you have different family of weaknesses, whatever it's fracture or it's layering, then you can isolate or break some piece of rock, and then hydrodynamic force, so lifting force from the river during floods, will be able to remove those detached blocks. So in that case, we'll speak of detachment or block plucking. So there are at least 3 processes. We can, people have been also proposed that cavitation can produce also some erosion, but people consider that it's mostly in waterfall that you can get cavitation, and in many other parts of the river, because overpressure due to cavitation are too small, it's not an efficient process. So it's mostly pebble abrasion, plucking, and sandblasting that people consider as important. So just a view of sandblasting with a link between erosional feature and the streamlines. So here, the particles are arriving that way with the streams, hitting this surface, and here, the water is producing some turbulent, stationary turbulent loop and making some particle, and the sand in particular coming back here. So here, making some erosion. So you have some different type of erosion on the lee side and the rear side of the river that produce some kind of asymmetrical shape. So it's typical that we can see in the river, and also fluid casts which are induced by a particular interaction between boulder shape and streamline. This kind of turbulent eddies or stationary turbulent eddies that even create what we call potholes. So when you create some small cavity on the bedrock, then you can have sediments like pebble that stay a good time in that cavity. And if you have a turbulent eddy, a stationary turbulent eddy, it will make the gravels to turn all the time at the same place, so heating and eating again that area and carving slowly this kind of feature called pothole. And the deeper is a pothole, the more prisoner are the pebbles at the bottom. And if a new flood is bringing new pebbles, then you will have always some tools to carve your pothole. So in some cases, you can dig very deep pothole, several meters deep. Another view of plucking. You can see here some sedimentary series which are highly fractured, and in that central part, the river flood had begun to partly remove or displace or dislodge this different piece of sedimentary layers. So next flood, probably this one, and this one will move by 1 meter, 10 meter, or 50 meter. So we saw that if we want to describe in a quantitative way the river incision, we need to describe the hydraulics. So we need to know, we need to know the channel width, the channel slope, the channel roughness. We need also to know the quantity of water going through the channel, so water discharge and velocity. If we consider that good part of the erosion is due to sediment load, pebbles, sand, then we need to know the sediment flux. But we need to know also the sediment size distribution. And we also see that we can have different processes depending on if the bedrock is fractured or not. So we need to know also the bedrock strength, the bedrock fracturing or familiar fracture, and we need to document the erosion rate associated to the different processes. Is the erosion of the bedrock due mostly to abrasion or mostly due to plucking? Depends on which river you are considering and which type of bedrock you are considering. So in some way, if we want to, on a field site, to document and try to address the issue of the bedrock incision in a physical sense, we need to measure all these variables. So to measure water velocity, so probably some of you are quite familiar with measuring water velocity in rivers. There are different techniques. So the traditional or historical one was to put in the water a profile velocimeter. So it can be like this kind of instrument, which is a pitot tube, which is immersed at different depth along a section of a river. Now For large river, they have other technique like acoustic Doppler current profiler, commonly called ADCP, which is based on the Doppler effect on acoustic wave sent in the river channel along 1, 2, 3, 4 direction. And by measuring the Doppler effect of the response of the reflected waves, we can have an idea of the horizontal velocity of the particles. So two cross-sections obtained through ADCP for the Ganga river at Harding Bridge in Bangladesh. So at high flood, you can see velocity up to 4 meters per second at the center of the stream, and here much lower than 1 meter per second at low flow outside of monsoon time. Or no, during low flow it's in July. So how does it work? The boat on which IDCP is installed is moving laterally along a section, and in that way you can get the velocity all along the section, and integrating the velocity, obviously you can get the discharge of the water. Measuring the bed load flux is slightly more tricky things. So the traditional method is to immerse at the bottom of the channel this kind of sampler. So one of the most common one is called the L. Smith sampler type. So you have a mouth, an opening here, and the gravels are entering during the flood in the opening, and they are blocked by the net behind. So the main limitation of this kind of instrument, it's for very big rivers, sometimes the flood is too high, so it's very difficult to get that kind of instrument down to the bottom of the river. And the second limitation, if you are in a stream, in mountain stream, if the mountain is moving blocks of 30 or 50 centimeter diameter, you see that with an opening of 10 centimeter, there's no way to get this kind of size into your sampler. So it's mostly used in gentle rivers, or not too steep river, and river that moves sand or gravels not too big. If you want to look at sediment load flux in a steeper channel, then you need alternative method. So one method is so it's a Swiss basin, a small basin, which has been instrumented. So some concrete dam or structure, more exactly. And along this structure, you can put some baskets. So when the flood is arriving with water, the water is falling down with the sediments, and the sediments are trapped into the basket. And then you can, after the flood, remove the sediment from the basket and weigh them to know what quantity of sediments you get. And another option is to put some sensor, like pressure or shock sensor, in a plate at the base of the concrete channel. So it's a metallic plate with a shock sensor below, and each time a boulder is hitting the plate, then your sensor will record the acceleration due to the impact. And by recording all the impact, you can get an idea of the sediment flux. So typically here, if I remember well, impulse in gray. So in gray, you have the impulse recorded by the plate, and in the black line correspond to the discharge. So you see that for these two two events, you have a close correlation between the discharge that move the bedload and the bedload impact. So if you get some kind of, if you are able to get some empirical relation between discharge and impulse, maybe, and if you compare with the sediment flux we get from the basket, then you can get an idea of the relationship from going from impulse rate on the place toward sediment flux. Based in the same principle, it means the fact that when some pebbles is hitting the bedrock is making some noise or acoustic noise, then a novel avenue of research has been to look for acoustic noise or seismic noise produced by sediment load during its transport. So this is the Trizori River. So Kathmandu is here in Nepal, and Trizori River is a large river going from South Tibet, crossing the high Himalaya, and going toward the Naryani River and Gandak River. And during a seismic experiment where they were mostly at the base interested by the crystal, the position of the Moho and the mantle structure below the Himalaya, they realized that during monsoon they had a very high seismic noise recorded by the seismic station close to the Trizori River. And in fact, you can see the profile of the river, and in red the high seismic noise. So you can see that there is a high seismic noise where the river is steep at crossing the high Himalaya. And the second thing, it's so this axis corresponds to the year, the months in the year, January to December, that the high noise is produced, seismic noise is produced between June and September during monsoon time. So this seismic noise is just the result of many impacts of the bedload on the bottom. And if you're able, through a model, an acoustic model, taking into account the bedrock in the area of the river, if you are able to link or relate the seismic noise or the amplitude of the seismic noise to the sediment load flux, then you get, by the records from your seismic network or seismic station, you will be, in theory, able to follow or track the bedload flux from your river during the monsoon. So it's going from seismic noise to sediment flux. It's not so easy. So it's, as I said, some avenue of research, and many teams are trying to make some theoretical and empirical relation between seismic noise and sediment load. Measuring bedrock incision. Several possibilities. So either the erosion has been very important. So it was the case, for example, after the Chi-Chi earthquakes in Taiwan in 1999, there was a nick point or a waterfall of 6 meters created just at the fault rupture. And this nick point has been retreating or receding quite quickly, so making erosion quite important, several meters of erosion. So in that case, you can measure this erosion by doing different topographic survey. It can be GPS survey, it can be LiDAR or radar survey, laser radar survey of the different position of the channel at different times. So here you can see it's in 99, September 22, and this is in 2010, the position of the channel bottom. You see like 20 meters of erosion. So when the erosion is so important, after an earthquake, so for example, then by classical survey, you can measure the quantity of erosion. You can do it also by using a terrestrial LiDAR, as I said, or you can do it also by using a unnamed aerial vehicle that will take several pictures of the zone and making some DEM or digital elevation model reconstruction from the different images. If you do it at several time interval, you will be able to reconstruct the topography at different time interval and making the difference between the different topography to reconstruct the erosion. So this case of figure is relatively rare, associated to specific events like after an earthquakes, and most of the time, erosion rate are only of a few millimeter. And a few millimeter or even less than a few millimeter, it's not possible to measure by comparing digital elevation model obtained, for example, from this kind of vehicles. And in that case, you need to go to have another method. So you can do, for example, as you say here, you consider a rule which is unshored on some fixed point. And by measuring the microtopographic change of the bedrock, you are able to measure a difference of a few fraction of millimeter and to document erosion of this amount. So this is an example in the sub-Himalaya, in the Shiwaliks. So you have a sandstone layer here. And along the sandstone layer, we document the erosion rate. So you see that above 2 meters above the water, there is almost no change, so no topographic change, so no erosion. But when we go close to the channel bottom, then we begin to see significant erosion from 0 to 10 millimeters per year. Yeah?
So in that image,
Yeah.
You're measuring a microtopography. A road is constructed over here, so it can be a engineering. It may be due to engineering structure, that microtopography.
It can be done on. You mean on concrete, for example, structure? Yeah, obviously.
So how you're measuring that? I mean, how can you use it for measuring that millimeter erosion rate?
So here.
Oh, yeah, in this
drill,
picture.
I don't have picture of, but you are drilling holes.
No. So in that picture, in last picture, there is a smaller picture, na? In this one. So you're measuring microtopography, na?
Yeah.
Okay, and then, but sir, a road is constructed, so it can be an anthropogenic activity. Man-made activity.
Yeah, it can be, but it's this. It's not a road. It's.
I think you said it's a road.
No, it's not a road. It's it's in Taiwan. It's a quartzite or I don't know. It's a quartzite or marble layer, which is perpendicular to the channel. So it's protruding in the channel, and there is no human action in that place. It's just
that
natural
was my confusion.
erosion.
I thought it's a man-made structure.
But obviously, if in that case, it's not man-made. It's only natural, and there is no human action. But you can also imagine this kind of technique if you have interesting at the outlet of some dam structure by some slurry channel or slurry pipe. You can also have erosion. So this kind of method can be used also to track the erosion of human structure. But in that case, again, it's human activity or it's pebble or sediment erosion due to when you are cleaning your dam. So it's the same process, except that the discharge of the flow, it's induced by human just to clean the dam. It's not a natural flow, but again, it's the same process. It's erosion by pebble. It's not people carving with a hammer or whatever.
Okay. Thank you.
So here, the same place where the microtopography has been measured. And you see, for example, here, during monsoon 2008 and 2009, the monsoon was not very important. And the maximum flood, the maximum water climbed to 5 to 4 meters. So relatively low flow and almost no erosion, topographic change, no erosion. In contrast, in 2006 or in 2007, the water climbed to 6 to 7 meters, so the flood was more important, remove more material, and you get more erosion as you can measure it along this sandstone layer.
So I did not understand actually. So here they're trying to understand when flood will occur, when the summer will be there, then it will erode the sandstone, right?
Well, it's the microtopography. I didn't
yeah.
say it. I mean, typically, you did. Let's say you are in the Himalaya, and so you do the measurement on May before the monsoon, and you do the same measurement at the same place on September or on October after the monsoon. So what you get is the total erosion during the monsoon. So by making the difference between the two topography. Yeah.
Okay. Topography. Measurement means like what kind of measurement? Like the thickness of the bed?
You have
label.
Some anchoring point. You place the rules exactly at the same place, and you measure the distance between your rules and the bedrock. So if you get some erosion, so initially you measure, 10 centimeters, and then 3 months later, after the floods, after monsoon, you measure at the same location, but now the distance is 11 centimeters. So you conclude that you get 1 centimeter of erosion of your surface.
Okay. So the two side, they will also go down, right?
No, because here it's that the rules is onshore on two holes which are drilled by 10 centimeters. Okay. And the reference where you are putting your rules, it's some fixed reference in the bedrock. Obviously, the erosion, it's not 1 centimeter, but 20 centimeters.
Okay.
You lose the holes, and it's no more possible to make some measurement. But you're right, you need some reference point, but don't move. So yeah, you cannot put your rules on top of the surface, because obviously you are misleading your measurement. Another way, with this kind of rules, you get just a discontinuous measurement and along a profile. If you want 2D measurement, you can use a high precision laser scan, what give you also precision, submillimetric precision, and so again, it's the same as previously. You need some reference point. So either it can be on the ground where you put the laser, or it can be some points on your block, bedrock you are studying. You are putting some holes, and then on the holes you will screw some kind of object, will be some kind of fixed reference. And once you get fixed reference, you can compare the two digital topography you will get with the scan before the flood and after the flood. So this is in Taiwan, and the laser scan on this kind of bedrock piece with two differential scan laser, they were able to document erosion going from 0 to 20 millimeter. And you see that on the upstream side of the blocks or of the bedrock slab, then you get high erosion up to 10, 20 millimeter per after the flood. And on this side, on the downward side, which is more protected from impact, almost no erosion. So with this kind of 2D laser scan, you can get a view of where you get erosion and where you don't get erosion. So if you do that, either the topographic line, the microtopographic line, or the 2D scanner, then you get an idea of the amount of erosion after a flood or after a monsoon season. But you don't know when the erosion is really occurring. So for that, if you're interested in the moment of the erosion, you need to develop an erosion sensor. One way to do that, it's to install a sensor into the bedrock. One way to have this, it's to drill a core in the bedrock. Then this core, you take out a piece, you cut it in two, and into the piece of bedrock, we install a small gauge, which is resistive lines. When it's glued again and installed into the bedrock and connected to a voltage recorder. So how does it work? If you get erosion of the sensor of the bedrock surface, you get at the same time erosion of this grid of resistance. And once you get erosion of the grids, then the resistance, the total resistance will be increasing. So by recording the voltage in your electric network connected to the resistance, you will be able to document the evolution of the resistance through time. The higher the resistance is, the higher the erosion of the bedrock. So two examples here in 2009 and 2010, again in the sub-Himalaya. So you can see that this is a voltage recorded, and this is 18 grid lines, 17, 16, 15. So here, after installation, we had 16 undisturbed green lines, and on day 211, we get a large flood that brought some sediment and created some erosion, and then the erosion was submillimetric, around 0.3 millimeter, and remove one grid line. So the resistance jumped from one value to the next value. And in 2010, again, the resistance and voltage evolution recorded by the sensor, and we go from a voltage of 0.2, then 0.4, and 0.5, and each step corresponds to some grid lines of resistance which has been eroded away at the same time of the rock. And from this voltage record, we can again, knowing the spacing of the green line, get some erosion through time. So the main information gained from this kind of record is that most of the time during the monsoon, you don't get erosion of the surface. And erosion of the surface is occurring mostly during a few hours during the maximum flood. So in fact, it's not very surprising, but it's what in some way we expect. But we get the confirmation that erosion is not done by small sand and silt and water during most of the time of the monsoon. It's done a very short period of time when the flood is maximum and able to remove and displace a lot of gravel and pebbles, and the heating by pebbles and gravels will create this erosion of the surface. So the synthesis of the river systems and measurement. So water discharge is relatively easy to measure. Bed load measurement, it's more tricky. So the community hope that with seismic noise monitoring, maybe one day we'll be able to document sediment load in a steep mountain, but for the moment it's some variable which is difficult to measure. I didn't speak about that, but rivers are transporting a very wide range of particle size from silt, sand, toward big boulder. So it's also quite difficult to document the moving of all these different particle size. In terms of bedrock erosion, we see that we can document erosion by topographic comparison. Now we can probably document also time variation. But for example, plucking detachment, it's difficult to document with some kind of sensor. So there are still some difficulties in monitoring on real time the erosion of the bedrock channel. And I show you also some quite interesting place where the erosion rate is high enough to be measured. So it is the case in Taiwan after the earthquakes because it's metric scale. It is the case in the sub-Himalaya because each monsoon you get a few millimeters of erosion. But if you go in a quieter, in a less active place, probably if the mean erosion rate is a fraction of millimeter per year, then anyway it will be very difficult to document this erosion over a period of 1 year or even 10 years. So there are difficulties. So to cope with these difficulties, one possibility is to go in the lab and try to reproduce these different processes and trying to make some parametric studies to isolate the effect of the different variables. So trying to reproduce river can be done by using flumes, and I will speak a little more about experimental study on the last day. So most of the flumes that have been used to document hydraulic process and sediment transport are straight flumes. So you can see, you introduce water and sediments and make some straight river, experimental river. And good part of the study have been done just at looking how the sediment are transported, but some researchers have been trying to use also this flume to look at bedrock erosion. So instead of putting some hard bottom of the channel, they put some slow cohesion or low cohesion cement at the base, and they were able to see after hours of experiment some carving of gorge or channels or inner channel into the concrete of the base of the flume. So a kind of experiment. So 2 images. So there are different experiments. At the top, experiment with a low sediment flux, 20 5 grams per second introduced at the upper part of the flume. And in this experiment, 215 grams per second, so 10 times, almost 10 times more sediment flux in this last experiment. On the left side, this is the color corresponds to the relative sediment concentration. In red, high concentration, a lot of gravels at the bottom of the channel. In blue or dark blue, almost no sediment cover. And here, this is the erosion rate of the substrate during 15 minutes. So it is in millimeter. So here in red, high erosion. In green or light blue, no erosion. So what do we learn from this experiment? When the sediment load is low, you observe a very low erosion. And when the sediment load is high, you observe or you measure much higher erosion of the substrate. A second point, it's in that case, we can see some isolated island of no erosion, despite the fact that there is some sediment load. So the two main conclusions we can get from this picture, it's first, it seems that qualitatively, the higher the sediment flux is, the higher is the erosion. So we need tools. We need tools to do abrasion. So more gravels means more impact, so means more erosion. But it seems that in some case, like here or here, if you have too much sediment concentration at the bottom of the channel, then it prevents the erosion. So it's just like having a cover of sediments that will protect or blanket the flume bottom and prevent erosion. So the same experiment, but seen this time is as total erosion on the flume versus the sediment flux. So a first experiment by Johnson, the one I showed before, another experiment shown made by Finnegan and co-author. And we observe what I said, the two conclusions from I drawn previously. First one, that increasing the quantity of sediment or sediment flux makes that you increase the erosion of your flume bottom. And second thing, it's if you increase too much the sediment flux, then eventually you can get some drop down to zero of the average erosion rate of your flume. For the following reason, at some stage you are covering or putting so much sediment in the system on your flume that you will cover completely the flume of sediments, and in fact you create a blanket of sediment that protect from any erosion, protect the bedrock from any erosion. So we evidence with this kind of experiment the dual role of the sediments. They are necessary as tool to create erosion. At the same time, if there is too much load, they can prevent erosion. So they favor and eventually they prevent erosion, depending on the quantity. Another option to look at bedrock erosion is to have not a straight flume, but an annular flume. So the advantage of the annular flume, it's you don't need to introduce at the top the sediments and get it at the bottom of sediments and recirculate and put again. Here, the recirculation is automated because it's a closed system. So the gravels are at the bottom of the flume, and just the water is the only element which is recirculated. So there is a system with a pump that sends water in pipes. The pipes are arriving here. They are making some injection of water at high velocity. This makes water turn into the flume, and water velocity and water entrain the pebble at the bottom. And you can put bedrock pieces and look at how the bedrock pieces will evolve according to the water velocity or according to the quantity of sediment at the bottom of the flume or the size of the sediments. I don't know if I have a picture. Yeah. So you see how the pebble will be moving by saltating, sometimes by rolling at the bottom of the flume. And each time the pebble is hitting the bottom, it can create some erosion. So this curve corresponds to a result, experimental result. So in red for 10 kg of sediment at the bottom of the flume, in blue for 60 kg of sediments at the bottom of the flume, and here on the x-axis, the PUMD charge. So the in some way, the higher is the PUMD charge, the higher is the velocity of the water in the flume, and obviously the velocity of the gravels. So you see that first, if you increase the velocity, you increase the kinetic energy of the pebbles. So in most cases, you will increase the erosion efficiency and the erosion rate. But for a minimal quantity of sediments, you see that we don't observe this increase, rather some slight decrease. So this is due to the fact that when you increase the velocity of the water, you increase the length of the saltation of the pebbles. And if you increase the length of the saltation, then you decrease the frequency of impact. And at some stage, if you go very high in the charge, the frequency can become very rare. So even if the impacts are more energetic and do produce more erosion, because they are rarer, because their frequency is much lower, then the total erosion they produce is lower. Second point we can see is that increasing the quantity of sediments, as we have seen for a straight channel, then increasing the quantity of sediment, we increase the amount of erosion. But as previously, we see that initially we increase linearly the quantity of erosion when we increase the quantity of gravels, and after some stage, we reach some kind of limits, and then we get again the blanket effect or the cover effect that makes that putting too much sediment in the systems at some stage limits, even sometimes prevent erosion. So in 2004, Sklar and Dietrich encapsulate these different effects in some kind of semi-physical model. They include the role of sediment as a tool for abrasion. They include the role of sediment inhibiting erosion when they are covering the channel bottom. And they include also the fact that increasing the water velocity and the pebble velocity, you can increase initially the erosion and potentially decrease it after some stage when the frequency of impact is becoming too rare. So they end up with this kind of relationship. Erosion rate is a function of shear stress or transport stage multiplied by a term that introduces the sediment flux. So the function is QS multiplied by 1 minus QS over QC. So QS is the sediment flux, and QC is the sediment transport capacity. So as long as the sediment flux is lower than the sediment transport capacity, so this term is lower than 1, and this term is positive, so we get erosion. If you introduce so much sediment in the flume, then the sediment flux becomes equal to sediment transport capacity of the river. So it's becoming 1 minus 1 equals 0. So if you are putting too much sediment in the systems, then the most of the channel will be covered by sediments and the erosion drop to 0. So here we have the two effects. Increasing the quantity of sediment increase the tools to make erosion, and increasing too much the sediment up to the transport capacity finally prevent erosion. So if we do a cross section like that, we'll end up, so QS over QC. So what we call the tool effect. So putting more sediments increase the erosion. And here the cover effect. Putting too much sediments will prevent erosion by some kind of covering effect. Sorry?
The QC is a function of shear stress or some other parameter?
Here,
QC.
in this diagram, we have two parameters. The two non-dimensional parameter, the shield stress here, as a proxy of the transport stage, and here the relative sediment supply, so the sediment flux divided by the transport capacity. So the transport capacity is depending on the shear stress, but in contrast, the sediment flux is some kind partially independent of shear stress, and may, in this kind of experimental device, is depending mostly on the quantity of sediment you are introducing in the sediment in the flume.
Okay, so I was asking because in this equation, this F shear stress, the function of shear stress is already there in this equation. So why there was a need to bring the another value as QC, because QC can be represented as a value of shear stress.
I'm sorry, I'm.
So in the equation, this is E and then minus K, and then again a function of shear stress. F.
Yeah, so
this
it's
is function.
in some way, well, I would have replaced the shear by the shear stress, but this equation is relative to the evolution along this line, and here, well, you're right. In fact, in the equation of the paper of Sklar and Dietrich, I put this equation just to give an idea of the different terms. But in fact, they have QS. We can recast this equation as
these equations look like a logistic equation, so that QC is the carrying capacity. See, QS 1 minus, it looks like a logistic equation term, so that QS can become maximum up to QC only, isn't it?
I'm sorry.
See, the QS can go up to QC maximum.
Yeah.
So that is like a logistic term. You know, if you want to grow something, and then you want to make it flat.
Yeah.
So it's yeah. So it looks like a logistic. No, but QS cannot go beyond QC.
Yeah, you are right on the fact that normally this function 1 minus QS over QC go to 0, and normally even QS cannot be larger than QC. But here, in fact, we can recast this equation as F2 multiplied by QC multiplied by QS over QC. So if you consider this variable, let's say, a dimensional variable QS over QC, so it's, so this is a function, and QC is a function of through transport capacity, a function of shear stress. So let's call it. So here we have a function, let's call it F1 of shear stress. So it depends only on shear stress. And here we have a function F2 of only of the non-dimensional function QS over QC. So if you consider a section like that for which shear stress or shield stress is maintained constant, then you are looking just at F2 function. So it's what I've drawing just before. And if you consider a constant QS over QC and you look at profile like that, so it's in logarithmic scale, so in normal scale it will be so no linear increase usually and something like that. So the erosion is a multiplication of these two functions and give you this 2D diagram. So I'm not sure to have answered your questions, but
Can QS become more than QC?
in theory, no.
So that's a typical logistic curve. It shows that something is increasing, and after that, the maximum it can go to QC.
Yeah?
So this is the, I think, the typical logistic type of.
Maybe I'm not familiar with the.
So we have a singularity is same. So QS is QC. That's the equilibrium point. That's the steady state. That's the stable equilibrium point. Then if QS is greater than QC, then also our system.
Well, in fact, QS can be. In fact, QS can be slightly higher than QC, but it means that in that case you will get alluviation. You will get piling sediments.
Yeah, I think so.
If QS is larger than QC, you will get sedimentation.
Yes,
alluviation.
exactly. The transport limited setting will come in, right?
But if you consider a reach, if the QS at the entry of the reach is higher than the QC, yeah, you get alluviation. But at a given point,
Yeah, then again, it reverts back to this setting that QS is less than QC. That's
Yeah.
what I understand.
yeah.
Yeah, this equation is for erosion. So, so on the basis of this equation, QS cannot be more than QC. But in reality, it can be more than QC. And whenever it will happen, then the process will be different. We will have the deposition process rather than the erosion process. Negative erosion is a deposition.
If you, I mean,
So E is the erosion. So it is a function of erosion.
if you are in this domain, you can have QS slightly larger than QC, but it means that you get sedimentation.
Sedimentation.
So you are piling sediments, and obviously erosion is zero.
Yeah.
Bedrock erosion will be zero. So yeah, we could extend up higher, but it will be zero everywhere. So the kind of semi-empirical relation that the author have used to define the model. So from different experimental study, they have been linking the velocity of the pebbles, the height of saltation of the pebble, the length of saltation of the pebble. They have related it to the shear stress or shield stress. And taking into account other results that experimental results that show that the erosion rate is proportional to the, for example, the angle of impact to the square. So the angle impact alpha is here. So if you are a vertical impact or normal impact to the surface it's relatively efficient in terms of erosion. If the impact is at slow angle, then the pebble will be bouncing without doing so much erosion. So the different kind of experimental results they have included and encapsulated in the model to get the picture I've shown you before. And here, the same diagrams with experimental result I get from this kind of circular flume or annular flume. In red, high erosion rate. In blue, low erosion rate. And exploring different quantity of sediment and different pump velocity, we can explore these 2D diagrams, and good part of the result display similar feature predicted by, or the feature predicted by the model. It means at low sediment quantity, low erosion. At high sediment quantity, we begin to cover the bottom of the channel and there is no erosion or very low erosion. And when we increase water velocity, we increase also the erosion. So at first order, the experimental result confirm the semi-theoretical model. For the highest velocity, we still have a very high erosion rate, whereas the model is predicting a low erosion. It's another issue. It's more or less, it's related to the fact that in the model, they are considering pebbles independently from the interaction with other pebbles. We will need a more evolved model taking into account the granular flow to probably reproduce the erosion at high sediment load and a very high transport capacity. This one is for the same grain size. So this is one of the interests of the experimental study. It's to be able to maintain some variable constant, like the grain size. And here we just change water velocity or sediment quantity in the flume. But in other experiments, we have been also changing and taking a different grain size. And I didn't put the result we had with different grain size, but the result is the higher the grain size is, the more efficient is erosion. So here, there are results for 1 centimeter pebbles. And if we take 0.5 gravels, 0.5 centimeter gravels, we will get a lower erosion. And if we take seems I have. Nothing happened. Oh.
I think I can put chair over.
Uh-oh. Yeah. 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 So taking 2 centimeter. Oh, it's. I don't know what's going on with there. It's probably my loading system. Yeah, so changing the gravel size will change also the erosion rate. And also changing the lithology. So there are experiments so in a slightly different device. It's a small tank, cylindric tank with a propeller that entrain water and entrain pebbles at the bottom. And by changing the lithology of the rock disk, Sklar and Dietrich were able to document large variation of erosion rate, 1 to 4 order, up to 5 order of magnitude in terms of erosion rate between a weak sandstone or an artificial cement and a resistant quartzite. And they propose some relationship between the erosion rate and the tensile strength resistance, so obtained by Brazilian test on rock sample. So it indicates that the more resistant is mechanically resistant is a lithology or is a rock, the more strength to erosion. So that makes the lithology much less erodible. So from the field and experiment observation, we were able to corroborate the positive impact of the shear stress and hydraulic power on the erosion, to document the role of the incised lithology, and also to document the dual role of sediments as a substratum necessary incision tools and also as a factor that can slow down the incision if the cover effect is important. So now we would like to go from this kind of field and experiment studies up to the broad scale and to be able to model river over the length of 10 or 100 kilometers. One of the difficulties is we have in the river different pebble size, different discharge, different sediment flux distribution between outward and inward channel. We have probably stochastic behavior, and all this complexity are making the, and without speaking about the fact that we can have abrasion and plucking, and today or in the previous slide, I spoke only about abrasion, and the number of quantitative study on plucking, it's much rarer because you can have very distinct cases depending on the type of fracture and strength of fracture or whatever. So all these difficulties makes that for the moment, people have not tried to really take the physicals or the physical model at the small scale and try to integrate over space and time at the scale of the river. So what do we do? So the other option is to consider some kind of broad-scale empirical model, and with the hypothesis that maybe we can study river by taking a few important variables like the channel slope, channel width, and discharge, and consider that all the variety of processes, sediment cover, stochastic variation, can be encapsulated in some average parameter. And most of the studies consider also that we can reproduce the erosion or the mean erosion done by river by some kind of morphogenic flood So instead of considering all the distribution of flood between low flood and peak flow, we will consider one single value of flood for a given reach of the river, and to be able to simplify the problem. So empirical calibration natural river. So I will show you a few theoretical consideration and also a comparison with natural system where people have tried to compare and calibrate this kind of empirical broad-scale model with a mean incision rate as deduced, for example, from terrace studies. So there are three main types of model that have been proposed in the literature. So the so-called detachment limited model, the transport limited model, and the what we could call hybrid model. So what is the detachment limit model? The detachment limit model postulates that most of the work done by the river in a mountain river, most of the energy expenditure available for doing some work on the channel bottom is going toward bedrock incision. It means that moving the bed load is just a teeny part of the energy expended by the river, and most of the energy is going toward detaching the bedrock. So for that reason, the most important point to a model is detachment limited, the detachment of the bedrock, and at the opposite, a transport limited model consider that most of the energy expended by the river goes for moving the bed load. And once you have moved this bed load, the sediment load, then you can have a small extra energy sufficient to cut the bedrock and inside the bedrock. So in one case, in the first case, then people relate the erosion of the bedrock to the stream power or to the shear stress, so directly to the energy expended by the river, because most of this energy is going to the bedrock detachment. And in the other model, transport limited model, we are close to some alluvial river, so for which most of the work done by the river is transporting the load. So in that case, we come back to the classical Exner equation used for alluvial river, which equates the change of elevation of the river to some by some conservation law, and which is the change of elevation of the river is depending on the divergence of the sediment flux. So the upstream sediment flux and downstream sediment flux. So if the downstream sediment flux of your ridge is higher than the upstream sediment flux, then you will be degrading and eroding your substrate, and at the reverse, you will be having alluviation, as mentioned earlier. So two different equations associated to different models to describe the broad-scale river. An hybrid model, it's considering slightly as taking the small-scale model of Sklar and Dietrich and expanded it to large scale, and considering that both detachment limited and transport limited, detachment issue and transport issue are important, and this kind of equation will encapsulate both the role of sediments, which are not involved here, and the role of shear stress and water expenditure, which are expressed in this second term. So to try to discriminate between these different models and try to see which one is the most adapted to describe a river evolution, we will see that people have tried different approach. So there are I just show you this first diagnostic, which is relatively simple, to see if your river is in transport limited or more in detachment limited. So if you are in transport limited, the river is mostly spending its energy to transport the bed load. So when you have, for example, like here, a natural dam made by a landslide, so it's along a Trans-Himalayan river in Nepal, you see these dams, and upstream of the dam, you see a lake that has been filled by sediments. And when you look at the topography of the river, you see that the slope of the river in that area, undisturbed river, is around 5%. And in the lake, or filled lake above, now the river is passing through, transporting the load through, you get a slope lower than 1%. So it means that to transport its load, the river needs a gradient of around 1%, but the long-term river slope is 5%. So it means that probably in that area, we are closer to the concept of detachment limited than to transport limited. Because if it would be a transport limited river, then all the river will be with a gradient close to the transporting limiting gradient of 1%. Okay, but it's just a qualitative argument. So I didn't mention, I mentioned just previously that detachment limited issue is related to the notion of expenditure, of energy expenditure. So let's introduce the stream power. So the power dissipated by the river, so the potential is the potential energy loss rate by, and can be expressed by unit of river length. So the potential energy is rho, the density of water by G by W by water thickness multiplied by Z, the elevation of the water parcel volume, and the rate of potential energy loss per unit of time, the derivative of E over time. It's this expression, so the same here. So dz over dt, which is dz over the derivative of z by x multiplied by the derivative of x by t. And dz over dx, this is a gradient of the slope, and this term, it's just the projection of v, the velocity of water. So the rate of potential energy lost by the water is just linked to the density of water, gravity, channel width, water depth, slope, and velocity of water. This whole term, WHV, it's the discharge. So we end up with the stream power of the expenditure of energy by the river is directly proportional to the discharge and to the slope. And usually, if we are interested by stream power dissipation per unit of channel width, we will introduce what we call the unit stream power, which is big omega divided by the channel width, and called usually small omega. As you see, omega is equal to small omega to rho g q, the charge was multiplied by slope divided by the channel width, and the shear stress was expressed previously as also a function of d charge divided by this width, channel width, to an exponent 0.6 multiplied by slope as an exponent of 0.7. So we have almost that's fine. It's just we have almost a relationship of type shear stress is more or less proportional to unit stream at the power 2/3. So we can, when we'll be speaking about detachment limited, we can jump easily from unit stream power to shear stress and vice versa. So because we are looking at broad scale, we are interested by average relationship and average scaling relation. So we can consider, for example, that discharge for a given region with uniform precipitation, discharge will be almost proportional to the drainage area. Usually it's slightly lower than 1, the exponent. Channel width, again, there are many variations along a channel, along a river, but on average, it is shown that channel width will scale with discharge or drainage area with an exponent close to 0.5. So if we introduce the scaling relationship into, for example, the expression of the stream power, so we are able to express both the stream power, unit stream power, as a function of just the drainage area, A, and the slope, with different exponents. So if we have the erosion rate proportional to the total stream power, we'll have M equal N, and potentially if the two are linearly dependent, equal 1. For the unit stream power, because we are dividing by the channel width, we'll have M equal to 0.5 and N equal to 1. And for the shear stress, because of this relationship, we will get M, or the exponent, over the area close to 0.3 and N close to 0.7. So the free relationship can, on average, be expressed as just a function of area, slope, multiplied by the coefficient. And in this coefficient, we can put what you want: lithology effect, precipitation, stochastic behavior of the discharge, or whatever. There are many variables encapsulated in this coefficient K, presumed to be uniform at the scale of a basin or of a region. So can we discriminate those different models? So first test to discriminate between detachment and transport limited model, and to see if one of these two or none of them is able to reproduce, for example, the shape of the river, the river evolution. So first test is just to look at maybe we can stop here because let's it's better. Yeah, it's better to stop.
Suppose if you have observed discharge along the channel, then do we need the scaling law or?
No.
Yeah. So the scaling laws are only used if we don't have the observed discharge.
Yeah.
And if we have the observed discharge, then these modeling schemes will become relatively easier. I mean,
easier, no, not easier, because one of the strength or the interest of this of a scaling, it's you can derive stream power over large area just by clicking on your preferred GIS software. But obviously, so it's the easiest thing. It's by using scaling law because, but it will be less precise. So if you have, for example, measurement of channel width, measurement of discharge, obviously you will be more precise than using scaling law. But it will be more time consuming to gather all this data together, and usually we'll have discharge on a few singles rivers, not on all rivers.
So we are looking for evolution, we are talking at a longer time scale. So if the modern discharge data is only an indicator, it cannot be used as a value for, you have to model the evolution, which may be incision rate or this thing, because that time period has seen the different episodes of climate change.
Yeah.
So these scaling law only provides a spatial variability, and we don't know exactly that how much those values were there.
Yeah, it's behind the scaling law and behind the use of a single discharge variable. Yeah, the main assumption is you consider some mean morphogenic discharge. So if the time of equilibration of your river is 1 million years, obviously Q corresponds to the mean discharge or morphogenic discharge over 1 million years, and will average climatic change over that period. If the time of equilibration is more like 100,000 years, then it will be the mean discharge over that time scale. Yeah. And obviously, when you have discharge value, it's measured over the 20 or last 50 years, let's say. So you are using this variable, but you are never sure that it's relevant for the last 50,000 years or 100,000 years. But it's better than nothing.
Same comment related to the relationship between long-term exhumation rate and the precipitation rate. So these precipitation rates are also derived from satellite images, which are average over 12 or 13 years or 40 years maximum.
Mm-hmm.
When you are relating precipitation rate with exhumation rate derived from fission drag or something, then there is also a problem of that scale. Like the precipitation rate does not remain same for few million years.
Yeah, but
you have matches.
Over the last 100 or 200,000 years, when you are comparing two regions with very different, very distinct precipitation due, for example, to some rain shadow, the main regime of winds and precipitation has not changed too much. So the amount of precipitation can be modulated by climatic change, but otherwise the global pattern over, if there is no major change in elevation of mountain or location of the continents, we can presume that the present pattern of precipitation is not very different or not so bad proxy of what's going on 1 million years ago. Except that maybe the precipitation were 20-30% higher or lower, and in some cases, in some places, we can have variation by 50 or 100%. But I would say in most places on world, the average modulation between different glacial, interglacial, it's by 20, 30, maximum 50% change in precipitation. And this is the total precipitation, and usually we are looking for total precipitation. But morphogenic or discharge, which do the job of making erosion, as I shown for the erosion sensor, you get erosion during one peak flood and a few hours. So there are small drainage basin. The Bakeya Basin, it's 350 square kilometers, so it's a small basin. So it's more like flash flood or almost flash flood with a big flood that lasts only 1 hour. And you see directly that erosion is done by some maximum flood that lasts 1 hour. And it can be completely distinct from the precipitation and average discharge over the whole monsoon. So you can decrease the total amount of discharge of the monsoon, but at the same time, if the weather is becoming more stormy, maybe you can get at the same time lower monsoon rain and at the same time higher rain during thunderstorms. And maybe it's, I mean, so the relationship between climate, average climate or annual precipitation and peak discharge, it's not linear. And it's, you can even have maybe some type of reverse connection. So it's, I mean, when you consider all the difficulties, all the complexity in nature, yeah, you end up with, oh, I cannot do anything. So for that reason, people have jumped toward more broad scale, average, considering that, okay, all these difficulties, we put it in coefficient K, and let's have a look if it works, or if it not works. And if it works, taking some simple assumption, why to go in more complexities?